Hold up your hand right now, in the dark, at arm's length. Look at the width of your smallest finger against the night sky, if you can see it from where you are. Astronomers have a strange and wonderful fact to offer you about that small sliver of darkness. In 1995, the Hubble Space Telescope was pointed at a patch of sky roughly that size, an area so small, so apparently empty, that some astronomers worried the 10 days of extraordinarily precious telescope time being spent on it would be wasted on a patch of nothing. It was a region near the handle of the Big Dipper that, to the naked eye and even to most ground-based telescopes, appeared to contain no stars at all, just blackness. The image that came back changed the way humanity understood the size of everything. That single patch of apparent emptiness, a sliver of sky you could cover with a grain of sand held at arm's length, contained not stars, it contained galaxies. Roughly 3,000 of them. Each one, not a star, but an entire galaxy, a collection of hundreds of billions of stars in its own right, sitting so far away that its light had taken billions of years to reach the mirror of a telescope orbiting 330 miles above the Earth's surface. That was one grain of sand's worth of sky. The entire sky, if you covered it edge to edge with grains of sand held at arm's length, would require about 10 million of them. 10 million patches, each one containing thousands of galaxies. Multiply it out, and the number of galaxies in the observable universe is now estimated at somewhere around 2 trillion. Tonight, we are going to try to actually feel the size of that number. Not just hear it, understand what it means, viscerally, the way you understand the distance to your own front door, or the height of a building you have stood beside. Because there is a particular kind of vertigo that comes from truly grasping cosmic scale. And it is one of the most valuable experiences the study of astronomy can offer a human mind. Not a fact to memorize, a feeling to have. And here is the strange part, the part that makes tonight's journey different from simply reciting large numbers. The universe does not merely turn out to be very large. It turns out to be, by every measurement we have been able to make, larger than the part of it we will ever be able to see. There is an edge to what is observable. There may be no edge to what exists. Let's begin close to home and work our way outward, one honest step at a time, until the numbers themselves stop behaving the way numbers are supposed to behave. Before we can appreciate how the universe grew, in our understanding, from a small and cozy place to something almost incomprehensibly vast, we should meet the person who made the first real measurement of any distance beyond the Earth. His name was Eratosthenes, and he lived in the 3rd century BCE, serving as the chief librarian of the Great Library of Alexandria, one of the most extraordinary repositories of human knowledge the ancient world would ever produce. Eratosthenes had heard a curious report from the city of Syene, far to the south, near modern-day Aswan in Egypt, that at local noon on the summer solstice, the sun stood so directly overhead that it cast no shadow at all, its light reaching straight down a deep well without touching the sides. In Alexandria, on the very same day, Eratosthenes knew this was not the case. He measured, using a simple vertical rod called a gnomon, that the sun's rays there fell at an angle of approximately 7 degrees from directly overhead. This small discrepancy told him something remarkable. If the sun's rays were, for all practical purposes, arriving parallel from such an enormous distance, which any reasonable astronomer of the time would readily grant, then the 7-degree difference between Syene and Alexandria could only be explained by the curvature of the Earth itself. The Earth was not flat. It was a sphere, and Eratosthenes had just measured a piece of its curve. 7 degrees is roughly 1/50th of the full 360 degrees of a circle. Eratosthenes knew, or had estimated with reasonable confidence, the distance between Siena and Alexandria, roughly 5,000 stadia, using the Egyptian unit of measurement common at the time. If that distance represented 1/50th of the Earth's total circumference, the full circumference could be calculated simply by multiplying by 50. His result, approximately 250,000 stadia, Converting ancient units to modern ones is not perfectly precise, since the exact length of a stadion varied somewhat between regions and eras, but using reasonable estimates of the units Eratosthenes was most likely using, his calculated circumference for the Earth comes out remarkably close to the actual value of just over 40,000 kilometers. Some scholarly estimates place his error at less than 2%, others place it somewhat higher. Either way, it stands as one of the most extraordinary feats of the ancient world, a measurement of the size of an entire planet, made using nothing but a stick, a shadow, and careful reasoning, more than 2,000 years before anyone would leave the Earth's surface to look back and confirm it directly. Eratosthenes had measured the first great distance in the story of human cosmic scale, the size of our own planet. Everything since has been an extension of the same basic method, comparing what we can directly observe against what geometry and careful reasoning tell us it must imply about distances we cannot directly walk. It would take nearly 2,000 years for humanity to measure the next major distance in this chain, and it required an entirely different tool, not a shadow, but the motion of the Earth itself. The distance from the Earth to the Sun is, in some sense, the foundational measurement of all cosmic distance. Astronomers call it an astronomical unit, and it comes out to approximately 150 million kilometers. Try to hold that number for a moment, the way the narrator of a bedtime story might ask you to. If you were in a commercial jet, cruising at a typical speed of about 900 kilometers per hour, and somehow able to fly in a straight line from the Earth to the Sun without needing to stop, land, or refuel, the journey would take you approximately 19 years. Light moving through the vacuum of space at nearly 300,000 kilometers per second makes the same journey in about 8 minutes. That is our first real cosmic yardstick, and once astronomers had it precisely measured, a task that took centuries of careful observation, including expeditions to observe the rare transits of Venus across the Sun's face from widely separated points on Earth, they had the base of a ladder that could reach much further outward. The next rung is the nearest stars beyond our own Sun. Here, astronomers use a method called parallax, which works on exactly the same principle as holding your finger at arm's length and watching it appear to shift position when you look at it first with one eye, then the other. Your two eyes, separated by a small distance, see your finger against a slightly different backdrop. The nearer the finger, the larger the apparent shift. Earth, in its orbit around the Sun, provides two vantage points separated by the enormous distance of two astronomical units, the full diameter of our orbit, depending on which side of the year the measurement is taken. Nearby stars, observed 6 months apart, show a tiny measurable shift in position against the much more distant background of stars far beyond them. Measure that shift precisely, and simple geometry gives you the distance. The nearest star system to our own, Alpha Centauri, sits at a distance of about 4.24 light-years. A light-year, worth pausing on carefully, is not a measure of time despite the word year appearing in it. It is a measure of distance, the distance light travels in a single year, moving at its constant speed through the vacuum of space. 1 light-year is approximately 9.5 trillion kilometers. 4.24 light-years, then, is a distance of roughly 40 trillion kilometers. If our jet from a moment ago cruising at 900 kilometers per hour tried to make that journey, it would take slightly over 5 million years. And Alpha Centauri is our nearest neighbour among the stars. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars, depending on how the fainter, harder-to-count stars near its edges are estimated. It stretches across roughly 100,000 light-years from edge to edge. Our Sun sits in one of its spiral arms, roughly 26,000 light-years from the galactic centre, a position that is entirely unremarkable, an ordinary star among hundreds of billions, in an ordinary arm of an ordinary spiral galaxy. To cross our own galaxy at the speed of light, the fastest speed anything in the universe can travel, would take about 100,000 years. The fastest spacecraft humanity has ever launched, moving at a tiny fraction of light speed, would take many hundreds of millions of years to make the same crossing. And the Milky Way, vast as it already sounds, is only the beginning. For most of the history of astronomy, there was genuine, serious scientific uncertainty about whether anything existed beyond our own galaxy at all. Through telescopes of the 18th and 19th centuries, astronomers had catalogued a great many faint, fuzzy, cloud-like objects scattered across the sky, objects that did not resolve into individual stars, no matter how carefully they were observed, that appeared as diffuse smudges of light rather than sharp points. These objects were called nebulae, from the Latin word for cloud or mist, and their true nature was a matter of genuine scientific dispute for well over a century. One camp of astronomers argued that these nebulae were relatively nearby clouds of gas and dust, contained entirely within our own galaxy, the same kind of stellar nurseries where new stars were known to form. Another camp, following an idea first proposed by the philosopher Immanuel Kant in 1755, argued that at least some of these nebulae were, in fact, entire separate galaxies in their own right, what Kant had poetically called island universes, vast independent collections of stars, comparable in scale to our own galaxy, but sitting at such extraordinary distances that their individual stars simply could not be resolved by any telescope of the era. The dispute became formal enough that in April 1920, it was staged as a direct debate at the Smithsonian Museum of Natural History in Washington, D.C., between astronomers Harlow Shapley and Heber Curtis. Shapley argued for the smaller universe, that the Milky Way was essentially the entire cosmos, and the spiral nebulae were relatively nearby, contained within it. Curtis argued for the larger one, that the spiral nebulae were separate, distant galaxies, and the universe was consequently far larger than anyone had previously proposed. The debate did not settle the question. Both astronomers made compelling arguments using the best evidence available at the time, and both, in different respects, turned out to be partially right and partially wrong about various specific details. The question was only definitively resolved a few years later, through the work we touched on in an earlier chapter of this series. Edwin Hubble, using the Hooker telescope at Mount Wilson Observatory, identified Cepheid variable stars within the Andromeda Nebula and used Henrietta Swan-Leavitt's period luminosity relationship to calculate its distance. The result, announced in 1925, was unambiguous. Andromeda sat at a distance far, far beyond the edge of our own galaxy. It could not possibly be a nearby cloud of gas. It had to be an entirely separate galaxy in its own right. The universe, in that single measurement, expanded enormously in the human understanding of it. It was not simply that Andromeda was far away. It was that our own galaxy, however vast it had already seemed, was merely one galaxy among what would eventually turn out to be trillions. Andromeda itself, we now know, sits at a distance of about 2.5 million light-years from Earth, meaning the light reaching your eyes if you looked at it tonight left that galaxy 2.5 million years ago, well before modern humans existed as a species. It is the nearest large galaxy to our own, and it contains roughly 1 trillion stars, considerably more than our own Milky Way. In roughly 4.5 billion years, our two galaxies are expected to collide and merge, a slow-motion cosmic event that will unfold over hundreds of millions of years and, current models suggest, will not directly destroy either galaxy's stars, given how much empty space exists between them even at their most densely packed. Once Andromeda was confirmed to be a separate galaxy, the question naturally became, how many others are there? And how far does it go? Here is something that deserves to be understood clearly, and that changes the entire character of what it means to look deep into space. When you look far enough away, you are not just looking at something distant, you are looking directly into the past. Light travels fast, but it does not travel instantaneously. It has a fixed speed, nearly 300,000 kilometers per second, and covering any distance takes time even at that extraordinary velocity. This means that every single thing you observe in the night sky, without exception, you are seeing not as it is right now, but as it was however long ago its light left it. When you look at the moon, you are seeing it as it was about 1¼ seconds ago. When you look at the sun, you are seeing it as it was about 8 minutes ago. When you look at Alpha Centauri, you are seeing light that left over 4 years ago. And when astronomers point the Hubble Space Telescope or the James Webb Space Telescope at the most distant galaxies they can find, they are not just measuring distance, they are looking directly at the deep past of the universe itself. This is precisely what made the Hubble Deep Field and its more recent, even more sensitive successors so extraordinary. The faintest, most distant galaxies visible in those images are not simply far away. Their light has been travelling for over 13 billion years to reach us. We are seeing those galaxies not as they exist today. Many of them may have merged, evolved, or been entirely transformed in the billions of years since that light departed. But as they appeared when the universe itself was young, in some cases less than 5% of its current age. The James Webb Space Telescope, launched in December 2021 and operating since, was specifically designed with this capability as one of its central scientific goals: to look further back in cosmic time than any instrument before it, by detecting the extraordinarily faint infrared light from the very first generation of galaxies to form after the Big Bang. In its first years of operation, JWST identified candidate galaxies whose light appears to have been emitted when the universe was only a few 100 million years old, pushing the observational frontier of cosmic history back further than astronomers had confidently expected the technology of this era to reach. This creates a genuinely strange and wonderful situation, worth sitting with for a moment before we move further outward. The night sky is not a single snapshot of the universe as it exists right now. It is a layered archive, spanning billions of years, with nearby objects showing you the recent past, and increasingly distant objects showing you an increasingly ancient one. Look at the moon, and you see the recent past. Look toward the edge of what our telescopes can detect, and you are looking at light that departed when the universe itself had barely begun to cool and form its first structures. There is no way to see the universe as it is right now, in its entirety, all at once. Every observation is, by necessity, a mixture of times, recent history nearby, ancient history far away, layered together into a single sky. And this fact, once properly understood, changes the very question of how big the universe is, because it means the size of the observable universe is not simply a matter of distance, it is entangled inescapably with time itself. Here is where the numbers begin to do something genuinely counterintuitive, and where careful, precise language becomes essential. The universe is approximately 13.8 billion years old. A natural first instinct might be to assume, therefore, that the furthest anything could possibly be from us is 13.8 billion light-years away, since light, the fastest thing in the universe, could not have travelled any further than that in the time since the Big Bang. This instinct is wrong, and the reason it is wrong reveals something profound about the nature of space itself. Remember, from an earlier chapter in this series, that the universe has been expanding for its entire history, not because galaxies are flying apart through space, but because space itself is stretching, carrying everything embedded within it further apart as it does so. This matters enormously for calculating distances to the most ancient light we can observe. When we detect light from a galaxy whose light left it 13.4 billion years ago, very close to the beginning of the universe's history, that galaxy is not 13.4 billion light-years away from us today. It was that far away, roughly, at the moment the light was emitted, But in all the time since, space itself has continued to expand, carrying that galaxy much further from us than the distance its ancient light might naively suggest. Accounting properly for this ongoing expansion, cosmologists calculate that the most distant light we can currently detect, light that has been travelling toward us for essentially the entire age of the universe, originated from matter that is now, at this present moment, approximately 46.5 billion light-years away from Earth. Not 13.8 billion, 46.5 billion. The expansion of space during the journey of that light has carried its source more than 3 times further away than the light travel time alone would suggest. This gives us the radius of what astronomers call the observable universe, approximately 46.5 billion light-years in every direction from Earth, making the full diameter of the observable universe approximately 93 billion light-years. Let that number settle for a moment, because it deserves to. 93 billion light-years is the diameter of only the portion of the universe we can, even in principle, ever observe. It is not the size of the universe. It is the size of our cosmic horizon, the boundary beyond which light, even if it began travelling toward us at the very first instant after the Big Bang, simply has not had time to reach us yet, given how much additional space has been created by cosmic expansion in the time since. And here is the detail that turns this from merely a very large number into something closer to genuinely unsettling. As far as every observation astronomers have been able to make can tell us, the universe shows no sign of coming to an edge at that boundary, or indeed at any boundary at all. Every careful measurement of the large-scale structure of the universe, the distribution of galaxies, the uniformity of the cosmic microwave background across the entire sky, the overall geometry of space itself, is consistent with a universe that is either genuinely infinite in extent or, at minimum, vastly larger than the portion we are capable of observing. Current measurements of the universe's overall geometry suggest it is flat or extremely close to flat to within the precision our best instruments can currently measure. And a flat universe under the standard cosmological model is generally understood to extend infinitely or so close to infinitely that the practical distinction becomes difficult to define meaningfully. We simply do not know, and current physics offers no clear way to find out whether the universe has any edge, any boundary, any point at which it stops. The observable universe has an edge, a genuine boundary, defined by the finite speed of light and the finite age of the cosmos. The universe itself, as far as the best available evidence can tell us, may not. If the universe extends beyond what we can observe, and the evidence increasingly suggests it does, possibly by an enormous margin, possibly infinitely, what, if anything, can we reasonably say about what lies beyond our cosmic horizon? This question sits at an unusual position in science. It is not merely unanswered, but may be permanently, fundamentally unanswerable in the strictest sense. Light beyond our observable horizon has not had time to reach us, and given the accelerating expansion of the universe driven by dark energy, it may never reach us at all. Regions of space are, right now, being carried away from us faster than light could ever cross the growing distance between us and them. Whatever exists there is not merely currently unknown. It may be permanently, physically inaccessible to any observation we could ever perform, no matter how far into the future human civilization, or any civilization, might persist. And yet physicists have not simply shrugged at this boundary and declared the question closed. Several serious lines of theoretical reasoning offer at least partial, careful speculation about what the wider universe beyond our horizon might plausibly look like. The most straightforward possibility, and the one many cosmologists consider most likely given current evidence, is simple continuation, more of the same. More galaxies, more clusters, more of the same large-scale cosmic web of filaments and voids that we observe within our own horizon, extending outward without any particular boundary or change in character, potentially without any limit at all. Under this view, the universe beyond what we can see is not fundamentally different from the universe we can see. It is simply more of it, stretching outward in every direction, indefinitely. A more elaborate possibility arises from a leading theory about the very earliest moments of the universe called cosmic inflation, a period of extraordinarily rapid expansion theorized to have occurred in a tiny fraction of a second after the Big Bang, during which the universe is thought to have expanded by a factor of at least 10 to the 26th power, an almost incomprehensible degree of growth compressed into an almost incomprehensibly brief span of time. Inflationary theory was originally proposed to solve several specific technical puzzles about the uniformity and geometry of the universe we observe, and it has since been supported by multiple independent lines of observational evidence, particularly patterns found within the cosmic microwave background. One notable feature of many inflationary models is that the process of inflation, once it begins in any given region, may not necessarily end everywhere simultaneously. Some versions of the theory suggest that inflation could continue indefinitely in some regions even as it ends in others, a concept called eternal inflation. Under this framework, our own observable universe might be just one region, one bubble, in the metaphor commonly used to describe it, where inflation ended and allowed the ordinary universe we observe to form while inflation continues elsewhere, potentially generating other similarly vast bubble universes, each with its own observable horizon, each potentially inaccessible to the others forever. It is worth being entirely honest about the status of this idea. It remains a serious, actively studied theoretical proposal, not an established scientific fact. It has not been directly confirmed by any observation, and some cosmologists have raised significant, substantive objections to specific aspects of how testable various versions of the theory actually are. But it emerges from the same theoretical framework, cosmic inflation, that has otherwise been remarkably successful at explaining features of the universe we can directly observe, which is precisely why physicists take the broader implications seriously enough to study them carefully rather than dismissing them outright. What can honestly be said without overstepping into unsupported speculation is this: nothing in our best current physics gives us any strong reason to expect the universe simply stops at the edge of what we happen to be able to observe from one particular unremarkable vantage point on one particular unremarkable planet orbiting one particular unremarkable star. The observable universe's boundary is a fact about us, about the speed of light, the age of the universe, and our specific position within it. It is very unlikely to be a fact about the universe itself. There is a clear and remarkably consistent pattern that runs through the entire history of human beings trying to measure the size of the universe, and it is worth naming directly because it tells us something about where we likely stand right now, at this exact moment in that ongoing story. Every generation, without exception, has significantly underestimated the true scale of the cosmos relative to what the following generation would go on to discover. Ancient astronomers, working with only naked eye observation, generally assumed the stars were fixed points on a relatively nearby celestial sphere, not much further away than the planets themselves. An assumption that placed the edge of the universe at what we would now consider an almost absurdly small distance. Early modern astronomers, equipped with the first telescopes, began to suspect the stars were considerably more distant suns in their own right, but had no reliable way to measure exactly how far, and generally still assumed the Milky Way represented the entire physical extent of the universe. Astronomers of the early 20th century, even after developing genuinely reliable methods to measure distances to relatively nearby stars, still debated seriously, as we discussed a few chapters ago in the Shapley-Curtis debate of 1920, whether anything at all existed beyond the boundaries of our own galaxy. Once Hubble definitively confirmed the existence of other galaxies in 1925, astronomers spent decades cataloguing them, gradually revising their estimates of just how many galaxies existed within the observable universe steadily upward as telescopes improved again and again, from thousands to millions to eventually the hundreds of billions, and now, with the most recent and sophisticated deep field surveys, to an estimated 2 trillion. Each generation, working carefully and honestly with the very best instruments and evidence available to them, concluded that the universe was some particular size, and each subsequent generation, equipped with better instruments, discovered it was substantially larger than the previous generation had confidently believed. This pattern is worth taking seriously as we consider our own present moment in this same long story, rather than assuming, as it is tempting to do, that we have now finally truly arrived at the correct and final answer. It would be a remarkable coincidence, given this consistent historical pattern stretching back over 2 millennia, if our own generation happened to be the first to have correctly and completely grasped the full, true scale of the cosmos. The honest, appropriately humble position is this: the observable universe, at 93 billion light-years across and containing an estimated 2 trillion galaxies, represents the absolute limit of what our current technology and our current position in cosmic history allow us to directly measure and observe. It is not, and there is no strong reason to believe it ever will be, the limit of what actually exists. We are, in the most literal and quite beautiful sense, standing on a small hill in a landscape whose true extent we cannot see from where we are standing, using instruments that let us see further than any human being in history has ever been able to see before, and finding, every single time our instruments improve, that the landscape simply continues on, further than the improved view can reach. There is a particular kind of vertigo that comes with truly holding these numbers in your mind all at once, rather than simply hearing them recited, and it is worth sitting with honestly before we close, rather than rushing past it towards some tidy, comfortable conclusion. 2 trillion galaxies, each one containing on average hundreds of billions of stars. A universe at least 93 billion light-years across in the portion we can observe, and quite possibly infinite beyond that boundary. A universe in which the very light reaching your eyes on any given night is, without exception, already old news. A message from the past, sometimes the very distant past, arriving at your particular location in space and time only now, this specific evening, after having crossed distances that render the word distance itself almost inadequate to the task. Against that scale, it would be entirely reasonable to feel small, insignificant even. A great many people, confronting these numbers honestly for the first time, do feel exactly that. But there is another way to sit with this particular scale, and it is the way I find myself returning to again and again on the nights I think carefully about just how large everything actually is. You are, right now, a small collection of matter, atoms forged, every single one of them, in the nuclear furnaces of stars that lived and died long before our own sun ever ignited, arranged through billions of years of chemistry and evolution into a form capable of doing something the vast majority of the universe, as far as we currently know, cannot do. You are capable of understanding, at least in part, how large the universe actually is. You are capable of holding the number 2 trillion in your mind, feeling its weight and recognizing that it describes something real, something out there, right now, whether or not anyone is looking at it. The universe does not know it is being observed. 2 trillion galaxies do not know, and could not possibly care, that a particular arrangement of atoms on a small planet orbiting an ordinary star has spent several thousand years of its short collective history slowly, carefully, patiently working out how big it all actually is. And yet that work has happened. It continues to happen right now in observatories and universities scattered across this one small planet. A species capable of measuring the curve of its own world with nothing but a stick and a shadow has gone on to measure the edge of the observable universe itself, and has done so with a precision that would have seemed like pure magic to every single human being who lived before the last 100 years. That is not a small thing. Against a universe of 2 trillion galaxies, it may in fact be one of the most remarkable things that has ever happened anywhere. Tonight, as you drift towards sleep, some of the photons reaching your eyes, if you look up before you close them, left their source before the Earth itself had even finished forming. You are, quite literally, looking into deep history every single time you look up at a clear night sky. The universe is very large, it is very old, and somewhere within all of that vastness, in one small corner of one unremarkable galaxy, something has learned to look back and wonder just how large it all really is. That too is part of what the universe contains.